In today's lecture, we are going to discuss about visualization of elevation model in 3-dimensional, delineation of watershed boundary, preparation of heat map, merging two contours layers into single layer. First, we will see how to visualize elevation data in 3-dimensional. For that, we need elevation information of our place of interest. So, we will download adjacent contours lines from OpenDem website. I open the downloaded file and extract it. Then we open QGIS desktop with grass, as we are going to use tools in grass and saga. In the QGIS, we will open downloaded contours. And define the projection. As this contours falls on Karnataka, I define WGS 84 UTM zone 43 north. Then using the projected contours, I will perform thin interpolation to prepare raster elevation data with a spatial resolution of 100 meters. Look at the result on the canvas. The created elevation data covers the larger area, which may take longer time to process. So I clip a portion of elevation data using clip tool, so the process may happen faster. I save this clip elevation data in the name of AOI, which stands for area of interest. The created raster data may have sinks and peaks errors in it, which may create problem during the delineation of watershed. To remove this error, I will use fill tool. The fill tool is located in the processing toolbox. In processing toolbox, I extend saga, then I extend simulation, then I double click on fill sinks tool. On the pop-up window, I define AOI data as input data and click on run. Followed by a click on close. Now we can see a result elevation data is appeared on the canvas as well as in the layer panel in the name of dem without sinks and sinks. We are going to use dem without sinks to visualize in 3-dimensional and to delineate watershed. To visualize elevation information in 3 dimensions, I click on view on menu bar followed by a click on new 3D map. Immediately we can see a window is appeared on the screen. Bring the window in the middle of the screen and enlarge it. We can see the elevation data which is added in the layer panel is visible here. For our better understanding, I will change the symbology of elevation data. Then click on Configure on 3D Map 1 window. On the pop-up window, define the type as dem, define the fill data in the elevation, then make vertical scale as 15 followed by a click on OK. Use tilt up, tilt down tool to tilt the image on the screen. And use move right, move left, move top, move down to move the image up and down or right and left. Use zoom and zoom out tool to zoom or zoom out the image and rotate the compass to rotate the image on the screen. We can also use wheel on the mouse to zoom and zoom out and pan tool to move the image on the window. Please go through other options available in 3D configuration pop-up window and understand it. Use tools available on the window to save the model in image format or to record video. To delineate watershed, I am going to use dem without sinks. To open watershed tool, I extend grass in toolbox, then extend raster. And I double click on r.watershed. On the pop-up window, define elevation as input, then define 2000 in maximum size of existed watershed basin. Click on help and look at the web page to understand all the available options on the pop-up window. Click on the run. Followed by a close. Look at the result on the canvas as well as on the layer panel. We have received several results. Among that, unique label for each watershed basin is delineated watershed. The result of watershed is stored in raster layer as we can see the pixels in it, and the spatial resolution of the pixel is 100 meters as our input elevation raster was 100 meters. We will convert it into vector and overlay on Google Earth to know how it is delineated on Earth's surface. To convert this raster data into vector, we should use raster to vector tool. The tool is available in grass, so I expand grass, then raster. In it, I double click on r.2.vec tool. On pop-up window, I define unique label for each watershed basin as input data and feature type as area. Then click on run, followed by a click on close. Look at the result on the canvas and on the layer panel. We have vector layer of watershed. I will save this as KML so we can open it in Google Earth. Go to saved KML file and double click on it. And look at the boundaries on the Google Earth. To get more accurate boundary and smooth boundary, reduce the spatial resolution of elevation data in tin interpolation. For this we have used 100 meter spatial resolution. You can use 50 or lesser than that to get more accurate boundaries. Heat map is a tool used to identify the hot spots using point input data. For this exercise, I am going to use a dummy boundary of a city and number of pickpocket incidents recorded in last 3 months. First, I will open boundary and pickpocket incidents layer in QGIS. Then we will look at the attribute table to know how many incidents are recorded. There are 3000 incidents are stored in point vector layer where the pickpocket has happened. By looking at the point location, we may not understand where incidents are happening frequently and where police should concentrate more to reduce it. To get the answer for it, I extend interpolation tool in processing toolbox. Then I double click on heat map. On the pop-up window, I define incidents as input layer and radius as 2000 and pixel size is 500. To understand the meaning of these entered values, click on help and go through the web page. Click on the run followed by a close and look at the result on the canvas and in the layer panel. It has resulted a raster layer. To understand the result more clearly, I will change the symbology and we will see. The green spot on the result indicates high concentration of incidents and pink spot indicates less concentration of incidents. Now we will see how to merge two adjacent contours into a single layer. First, I will download two adjacent contours from OpenDem. The files are downloaded in zip format. I will open it in a folder. Then I keep this in a single folder so I can easily access it. I create a folder in the name of contours. Then inside of it I am saving it. Then I am extracting the files from the zip folder. And I am opening this extracted file in QGIS. Now we can see single layer of contour. I am opening the second one. Now we can see the adjacent contours of two layers. To merge it, I go to vector, then merge vector layer. Then I click on the three dotted buttons on input layer. Then I select both the layers as input. Then I define coordinate system as WGS 1984. As our both input data are having the same coordinate system. Then click on run, followed by a click on close. Look at the merged data on the canvas. Now we can see the two separate layers are merged into a single layer. We will look at the coordinate system of our merged data. Downloaded data is having only geographical coordinate system. So we will project it and we will save in a new name. I am saving this in the name of merged. And defining the coordinate system of WGS 84, UTM zone 43 as these areas are falling on Karnataka. I open the merged data on the new canvas. Now we can see the coordinate information of data. It shows WGS 84, UTM zone 43 north projected. Using this data, I am going to create the elevation model. To create the elevation, I am going to use tin interpolation, which is available in interpolation toolbox. Here I provided merged data as a input data and elevation attribute field as a elevation field, and I have selected the structural line as a type. Then I am using layer extend of our merged data. Then pixel size as 500. Look at the elevation model on the canvas. We have created this elevation model merging two contours. So if your study area falls more than single scene of contour, you can download all the contours, then you can merge using merge vector layer option. In today's class, we have discussed about how to visualize elevation model in 3-dimensional, how to delineate watershed boundary, how to prepare heat map, and how to merge two contour layers into single layer. To know more about techniques used in the class and related information, visit www.qgis.org.